So at this point, we're coming to the end of Physics 30, so we just kind of want to summarize one of the grand things that you've learned over the course of Physics 20 and Physics 30. So in the course of both of those classes, we've talked about all four of the fundamental forces. So the four fundamental forces, to recap, are the electromagnetic force. We looked at that through Coulomb's law. The weak nuclear force, we were looking at that through the conversion of quarks in beta positive and beta negative decay. We have the strong nuclear force, this force that kind of binds our nuclei together. And then we have this gravitational force we would have looked at in Physics 20 using Newton's law of universal gravitation. So we always talked about the range. So we said that the electromagnetic and gravitational forces, because of that proportionality to 1 over r squared, they do have an infinite range. The further away you get, the weaker they get, the forces, but they are still present. Just because we're very far away doesn't mean the force is zero. It's small. We also talked about the relative strength of the forces. So we said if we kind of define strong nuclear as the strongest, we'll call that a 1. Everything is a little bit weaker than that. So electromagnetic's about 10 to the minus 2. Weak nuclear is about 10 to the minus 6. And then the one that really stands out, gravitational, we got 10 to the minus 38. So gravitational force is the weakest of the four fundamental forces. But again, the reason we notice it on Earth is because the Earth also has a really large mass. So just to quickly go through our four forces. So yeah, that electromagnetic interaction or force, it acts on any particle that has the electric charge. And this force of interaction, again, we've described using Coulomb's law. So the weak nuclear force has to deal, it acts on protons, neutrons, electrons in order to bring about beta decay. And depending on what we have, so we're going to change from a D to a U quark in beta negative decay. We're going to change to a U to a D quark in beta positive decay. And of course, this force doesn't have infinite range. It's only got about a range of a few atom meters, so about 10 to the minus 18 meters. So it's really, really short in terms of its range. The strong nuclear force, as we mentioned, it acts on protons and neutrons to keep them bound to each other inside the nuclei. And that force has a short range of about a femtometer. So again, it's very strong on a limited range. And then of course our gravitational force or gravitational interaction, this is that force of attraction between two masses that we use to describe, or that we use Newton's law of universal gravitation to describe. Now, the thing with the gravitational interaction is we've used Newton's law of universal gravitation to describe it. It does a pretty good job for what we need, but it's not actually the complete picture of gravity. If you want a more thorough understanding of gravity, this is where you have to go to Einstein's theory of general relativity, which is well beyond the complexities of high school. But if you do study physics at a later date in post-secondary, it's certainly worth taking general relativity if you get the opportunity. It's really hard, but the things you learn are so fascinating. Now, the last thing we just want to talk about is this thing called the standard model. So if you've taken a biology class, you know that to build life, you need DNA. And then to build DNA, we need the four nucleobases. So we need adenine, guanine, cytosine, and thymine. Well, we could kind of take that and extend it to the real world. So in our universe, everything is made up of particles. And we know that some of these particles are, once again, they're fundamental. They don't have any quarks, which we cannot break. And these particles are ones that we can't break down any further. So these building blocks, these fundamental particles, these make up what is known as the standard model. So let's have a look at that. So this is the standard model for elementary particles. We can see our 6 quarks, we can see our 6 leptons, we can see this gluon. So a gluon, I'm oversimplifying it, but think of it as kind of like the glue that holds quarks together. So we have our photon, the carrier of the electromagnetic force. We have our Z boson, which is going to be the carrier of the strong nuclear force. We have our W boson, which is the carrier of the weak nuclear force. And we also have this Higgs boson, which I'll talk about in a minute. One of the things that's missing in the standard model is this carrier for the force of gravity. This is what we call a graviton. We haven't seen any evidence for it yet. That doesn't mean it doesn't exist. It's just the evidence hasn't come about. The other thing you have to understand is particle physics has evolved significantly in the last 50 years. So this standard model, this is what we know of to date. Will it change in the future? Most certainly it will. But this is our best understanding to date. The last thing I just want to mention is that Higgs boson, and this was in the news a lot about not even 10 years ago. This was the big kind of talk with the Large Hadron Collider. And basically what Higgs proposes is that particles themselves, they don't actually have mass on their own. What they do is they actually acquire this mass by interacting with this thing called the Higgs field. And this Higgs field is said to permeate through the entire universe. So what the Higgs boson would do is it would be used to transfer mass between that Higgs field that permeates the universe and every particle that we have in existence. And then, of course, different particles would be affected by the Higgs boson in different ways. So on July 4th, 2012, it was announced that that particle that had the correct properties, like mass, no charge, no spin, was discovered. And this was consistent with the theory of the Higgs boson that was proposed by Peter Higgs many, many years ago in the 1960s. So the discovery of the Higgs boson, like the experimental evidence finally catching up with theory, this was considered a major advancement in particle physics, and it was kind of the last holdout of the Standard Model. So for the contributions to particle physics, Peter Higgs and François Englert, they were awarded the Nobel Prize in Physics. And I cannot emphasize enough this discovery, this experimental evidence of the Higgs boson. I cannot emphasize enough how much it had actually advanced the discipline of particle physics. So in the last 10 years, this has probably been one of our biggest discoveries in the field of physics.